Welcome to the Organic Chemistry video content to accompany the Organic Chemistry lecture guide and the Organic Chemistry primer. Problems in this video come from Part 1, Structure, Stability, and Conventions. Our first problem asks us to provide structures given the IUPAC names. A good place to start is to figure out what the parent chain is, in this case nonane, a 9-carbon chain. Once you've drawn that parent chain and numbered it, it's just a matter of filling in the substituents. An ethyl group on position 5, methyl groups on positions 2, 3, and 4, and we have our correct structure. In our next example, the parent chain contains an alcohol. Our parent chain is 3-hexanol. So we have to draw a hexane chain with an OH on position 3. Then it's just a matter of filling in the methyl group at position 2. And there is our structure for 2-methyl-3-hexanol. In our final problem on this page, we have as a parent chain cyclohexane. Since cyclohexane is cyclic, we don't have to start numbering from the end as we would with a linear molecule. Any carbon can be carbon number 1. We have substituents on carbons 1 and 2, a chloro and a methyl group. The last thing we have to address is this cis label of configuration at the front of the name. The cis label indicates that both groups are pointed the same way. We could draw both of these as wedges or both of these as hash lines. In this case I'll choose to use wedges, and that is a correct representation for cis 1-chloro-2-methyl-cyclohexane. In our next example, we're first asked to define the term conformational isomer. A compact definition would be structures differing only by rotation about single bonds, and which can be interconverted without bond breakage. The next part of this problem is for us to draw the most and least stable conformational isomers for butane. So first we figure out what butane is. It's a 4-carbon long chain, and we want to use wedges and hash lines or Newman projections to accomplish this. So we can set up a little table here, and if we start off thinking about, well, what would the most stable isomer be using wedges and hash lines? Well, we're going to be rotating around this bond, and we have 2 H's on this carbon and then the CH3. And the same thing on this other carbon, 2 H's and the CH3 at the end. The most stable way that we could arrange this molecule is to keep those large CH3 groups as far apart from one another as possible, anti to one another, CH3, CH3. Each of these carbons is a tetrahedron, so we need to fill in our H's, one towards us and one away from us, and that would be the most stable conformation for butane. The least stable conformational isomer would be one in which those two CH3 groups were syn to one another, both pointed the same way, so that you would have the greatest steric hindrance or repulsion between those two groups. And then if we just make sure that we fill in the tetrahedral shape of the other two carbons, we have the wedge and hash line representation for that. And the next part of the problem, part B, is to draw Newman projections of those conformations. We can set up the Newman projection drawings by drawing in one side of the conformer. So here I'm representing one side as the front. If my CH3 is pointed straight up, as it is in these cases, and I look at the back of the Newman projection, what I need to represent in the back, I see a CH3 pointed straight down. And then the H's are pointed at diagonals coming towards us or away from us, or at angles not directly syn to the CH3 group at the top. And that's different from how the least stable isomer looks. In the least stable isomer, my CH3 is pointed straight up in the front, but it's also pointed straight up in the back. So I should have a CH3 eclipsing that CH3 in the back. I have an H at a diagonal coming towards me in the front, and in the back I have an H pointed the same way. Likewise for the one that's drawn as the hashed line on the front and back, they will be eclipsing each other. We will apply the same concepts to determining the most and least stable conformational isomers for 1,2-dibromoethane as we did for butane. first we need to draw the molecule and set up our Newman projections. So here is 1,2-dibromoethane, and if we look at the two sides, this side and this side, each side has a bromine and two hydrogens. We can fill those in on the Newman projection scaffolds I've drawn below. Now if I'm looking for the most stable conformation, I want to keep the two large groups, which are the bromines, as far apart from each other as possible. Those are what I'm going to focus on. I will want that bromine with its lone pairs, a much bigger atom than a hydrogen, to be as far apart as possible from the other bromine. So in the back, that means the hydrogen atoms will have to stick out in the staggered conformation. On the other hand, if I want the least stable isomer, again, I'd want to put the two large groups eclipsing one another. So the two bromines would be eclipsing one another at the top in this case. We go about this problem concerning ethylene glycol in a similar fashion. First drawing the molecule, then identifying attractive or repulsive forces. The OH group is unusual compared to the other groups we've looked at in previous problems in this video, because an OH group can engage in hydrogen bonding with another OH group. That would be a very attractive interaction, so we might want to have OH groups close enough to one another that they could hydrogen bond with one another. So with that in mind, we can start drawing the different conformations where the OHs are as close together as possible, move them 1 unit away, move them 2 spaces away into another eclipsing conformation. And we would suspect that the conformation in which they are close but not completely overlapping would probably be the most stable conformation, because you can have the attractive force there, but you won't have the problem with the lone pairs on the oxygens engaging in a lot of steric repulsion with one another. This would then be the most stable conformation for ethylene glycol. This question asks us to draw all of the conformational isomers for this compound, rotating around the bond indicated, front versus the back of the Newman projection, and then to assess the relative energies of these species. Let's start by drawing the back part of the Newman projection for all of these, and we can just go about rotating the front part. So I filled in the back part of the structure, keeping the H's at the top and bottom right, bromine at the bottom left, as it was in the original structure. I'm going to undertake just rotating the front in 60-degree increments. Every time that front rotates 60 degrees, alternate between staggered and eclipsed conformations. It starts off being staggered. So we're going to go to an eclipsed and then alternate around staggered, eclipsed, staggered, eclipsed. And now it's just a matter of moving the front ethyl group and hydrogens around the ring. I find it easiest to focus on one group, hopefully a unique group like the ethyl group here, and if we just fill that in, rotating 60 degrees in each spot, the ethyl group will process all the way around the ring until we get back to the original structure. And all the other spots are filled in by the hydrogen atoms that we can add after the fact. Having drawn the conformers, we can then assess which of these is going to be the least stable. To do that, we find the largest group on the front and the largest group in the back, the ethyl and bromo, and identify when they will be the closest together. That's your highest energy, least stable structure. Your lowest energy, most stable structure will occur when those two units are as far apart as possible in a staggered conformation. The staggered conformations are the local minima. So the other staggered conformations where we have the ethyl and the bromo that are gouged to one another, those 3 cases, will be higher in energy than our most stable, but they will be lower in energy than any of the eclipsing conformations. So I've labeled those 3 positions with a G to indicate those are the ones which have a gauche interaction between the ethyl and bromo groups. Finally, we have these other eclipsing conformations where the bromine and hydrogen are eclipsing one another, and that's not as bad a steric hindrance interaction as a bromine and ethyl group. Those should be lower in energy than our least stable conformation over here, but still they'll be higher in energy than our staggered conformations. So they'll be somewhere in here. Finally, then we can draw our curve. As we go from the gauche conformation we started with, we'll have to go up in energy to push these two groups closer together, and then the energy will go down as we go back to a staggered conformation, up as we go back to an eclipsing conformation, down to the gauche, finally up to the least stable, which has the bromine and the ethyl group eclipsing one another, and then down to this other gauche conformation. So, while not quantitative, we didn't try to figure out exactly how much different the stability would be. This shows us the qualitative relative relationships between the energies of all these different conformations.